guess it is.
Well, just tell her to start digging a hole, see if it matches up with her theory.
Have you seen their map? I always thought it was like the pull-down map, like how we always see it, but it's not. They have the North Pole in the center of their map, and then the South Pole is the entire boundary of their map. So Antarctica is the boundary of their whole entire map. So there's a YouTube video where they take a magnet and they put it in the North Pole, and then they take a compass and go around it and say, look, it always points to the north and always to the south, so it's got to be true. And I'm like, well, that magnet that you're using isn't a North Pole, it's a North and South Pole, which is why it's doing that. If you were to hold it like this and go around, it would point straight up. So now I've got to make a YouTube video to prove it wrong. Now it's my life goal now to prove that the Earth isn't flat.
Advertisement?
Huh? I was creative enough. I'd just be one.
Advertisement of the sun?
Yes. Before we go to,
Come up with a decent excuse for it.
can you please distribute it? It's like 4 pages per person, and it should be enough for each of us. So today, John will practice his doctoral thesis talk, and before I will quickly go over the things that we started last time but didn't finish. So it's about getting to Sunnyvale, yes.
I registered early.
Did you register?
Yep.
Okay, and it works. You check that it works without paying, right?
Yeah, I did the same thing as last year. So they need to have confirmation in writing 2 weeks prior. So if I'm not going to be able to go, I'll just have to send them a letter by the end of January. It should be okay.
Okay. Yeah, I think it is a good plan for everyone. And did anyone else register? You did? So navigate, if there will be any newcomers, I will navigate them to you as experts in registering for free. So last time we did finish at registering, and here are the titles that you may use for including as a keywords in your abstracts and in titles to.
That's different sessions or what? These
It's a conference on all the subjects,
all the subjects.
but they will be mix and match.
Okay, so it's not going to be like separate sessions.
No, it may be will be one invited talk on probably it's just titles of invited talks, and simple people will do contributed talks or posters that more or less match this stuff. So the error registration on November 30th is, here's how to register. It was recently updated. So if you attend,
Oops. They just restarted the whole system. You have to.
Oh, weird.
this is our favorite part of the meeting.
Wow.
Especially see it.
Yeah.
There is a
Wow.
finite speed of light and going through circuits.
Enjoying that stuff.
If you attend this conference like more than 5 times, you'll start getting personal invitations. Not to forget about it. So upon you register, you will get the link where to submit the abstract. If you didn't like they want to prevent submission without registration.
Ah, that's the way it goes.
Yes. Otherwise, the system
first you register and then there's going to be a link.
Otherwise, the system will be flooded. So, and if you go on the So prepare for surprise if you didn't register, if you didn't submit the abstract. If you did, you're fine. Is there anyone who didn't submit the abstract?
I didn't submit mine yet.
Oh, okay. So when you go to the abstract, you select for the Sustainable Symposium, and you think everything will be normal. You just create your name and password, log in, click on to submit the abstract, type in the title, select whatever. If you're typically we are hunting for posters, but plenary and invited goes only with invitation. But some of us were very brave last year and submitted for oral contributed, like for advanced scientists.
Brave or naive.
It worked?
Yes.
Really?
So
To get the oral?
Dane got an oral presentation 2 months after he joined the group.
Yeah. And I got introduced as a doctor.
Yeah. So if you want a little bit more of honor, and if you want people torturing you with questions in public rather than one-to-one poster, you can select this oral contributed. But then after you click here, submit the stuff, they will check that you are a real human. So they want to select. Well, maybe questions are different. For me, it was identify which part of the image are street signs, and then you get things registered, and probably it will be placed in the book of abstracts. Okay. So as a backup, I can bring up the PDF of thesis if the connection goes slower than we want. But I hope that there will be no problems with connection, and John will take over and forward his content to our screen. So please do it. We have time until 6 for recording things. Please make notes on this piece of paper. Be as critical and aggressive as you can. It's better to experience it now rather than during the formal defense, which is in 2 days. John, floor is yours.
Okay. All right. Is it full screen for you guys?
It's black screen for us now.
Okay. Hold on. Then I'm going to do this differently. All right. Now is it full screen?
Yes.
Okay. All right. Well, thank you guys for coming to listen one more time through this practice talk. So the title is Non-Adiabatic Dynamics in Quantum Confined Semiconductors. And so just briefly what I will be going through. I'll give you a little bit of introduction and motivation as to why we're looking at these topics, and then a look at the methodology of how we're interested in studying these topics, and then going into some more of the specifics for the chemical systems of interest for us that we've looked at over the past couple years, and then we'll wrap it up and try and conclude with some final thoughts. So one of the main things we're interested in are electronic processes for applications that take some type of solar energy or renewable energy conversion. And so things such as photovoltaic cells, photocatalysis, things that harness a chemical composition of a material to take the energy from a photon and turn it into electrical energy, which we can use for our day-to-day living. And so some of the other opportunities for use of semiconductor materials are for optoelectronics, different light emitting devices, basically the inverse process of what capturing solar energy is. And so there are different types of electronic processes that can occur following some type of photoexcitation in which we're interested in. One thing to know is that for multiple different types of relaxation mechanisms within the same system, they're all going to be competing with one another. So it's important to know what types of mechanisms may occur, what the relative timescales are, so we can kind of determine what type of event may be more probable than the others. And so just
Oh no.
So it's happened.
Therefore, we do not have Skype defenses.
So you defend on Thursday this week?
Yes.
It's John's side or our side? Having problems.
It's his side.
His
Because
side?
he's on, he's sitting on a couch, which means he's on wireless. And second, he's using home internet, which depends on the company. I'll send him an email just in case he didn't realize that he's not on
Yeah.
So maybe okay. So now he realized that he is not connected and he will reconnect back.
You are the only participant in the conference.
So our backup solution, if John did, he was planning to drive here, but the roads were icy, and we decided that it's safer to stay alive before the defense.
Okay, I see.
So if he didn't connect at all, we just sit and read his slides. I can try to present instead of him, but it will not help him.
We can put him on the speakerphone, you know, he can call
Yes.
and then
Yes.
just look at his
This-
slides.
Okay. Thanks for coming.
Yes.
Now everyone is here.
Oh, that's trippy.
You know this effect, right? You freeze and you didn't reconnect.
Okay.
So if you were speaking for last 5 minutes, we didn't hear it.
Oh man. Okay.
So please try to reconnect, and if as a backup, if it will not work, you just speak through Skype.
I thought I was doing so well. No one interrupted me or anything.
You were thinking I am so perfect.
Okay. I was gonna say. I mean, I'm even.
Oh, okay.
Now I'm redirecting to the web page. I'm gonna plug back in a second.
So if you're bored to wait until technical things are resolved, you can just read and develop comments, because yeah, it sounds like connection problems, not the software.
Sure, even through the cell phone,
Through
3G doesn't work.
no, it is Skype. Cell phone is the last resort.
Okay. Oh hey.
Okay. All right. Can you guys hear me?
Yes.
Yes.
All right.
You should ask it after each slide.
Okay. Well, maybe what I will do then is. Okay. Well, can you still see the slides here?
Yep.
Okay. Then I'll probably just, I'll probably do it this way. That way I can kind of see if things are moving on.
Okay. Yes.
We lost you
Yeah.
on slide 5.
Yep. Okay. At the beginning of slide 5 or at the end of slide 5?
Probably the beginning.
Okay. All right, where was I? Okay, so I was talking about different types of electronic processes occurring in photovoltaic and optoelectronic devices, and the fact that we're interested in these type of mechanisms because they can dictate or predict what's going to happen, and if we make a material modification, can we make that process more efficient? And so here on this slide, we're looking at 2 cartoon pictures that highlight a number of different electronic processes that may happen in a material. In the left figure, there's a blue vertical arrow going up, representing some type of absorption. And then there's also various arrows coming down. So black squiggly lines represent some type of non-radiative event, whereas colored lines going down represent radiative. And so internal conversion or electron cooling or non-radiative relaxation are a number of names for this type of process, which we're interested in and we're able to calculate. And so other types of radiative processes which we're interested in are fluorescence. And because we're looking primarily at non-spin polarized materials, these are the two processes that we would say occur most readily. And then in the picture on the right, there's a couple different highlighted processes. So you see the very first one on the left with an R cooling. So this is the same type of non-radiative relaxation where there's just an excited electron that loses its energy through vibration and relaxes down. A second type of excitation or event that can happen is there's an excited electron, but instead of losing its energy radiatively or non-radiatively, it promotes a second electron up. And so you're taking one type of excited charge carrier and turning it into two, also known as some type of or multiple exciton generation. A third option is you can have a high energy excitation, and before any type of relaxation event occurs, this charge can be collected out either through a secondary material or directly to an electrode, which can increase the photovoltage of the process. So those are the things that we're interested in and kind of the why as to what we're excited about. And so the next thing is how are we looking into these types of events? If you want to measure ultra-fast events and different types of electronic processes, it can get to be a very expensive lab setup and something that can be very hard to do. So the approach that we've taken is we're using computational methods and computer softwares to look at a range of these electronic relaxation mechanisms in a number of different materials rather than spending years setting up and perfecting one type of measuring technique. So the first thing that's going to happen is we'll find a problem or material that we're interested in, and we'll be able to build a model of it. And so we'll take this computational model and place specific atoms in an arrangement that simulates the chemical system, and we'll want to optimize this structure. And so the optimization is a process in which all the atoms are shifted slightly, and an energy is calculated. And so every time the atoms are shifted, the energy gets recalculated, and this is done repetitively until the lowest possible energy configuration is found, or until the total energy hits some sort of threshold that we're happy with and we think is close enough to the lowest energy configuration. And so these total energies are dependent on the locations and the densities of the electrons, which are also are dependent on the atomic positions. And so finding the optimization provides the total energy, but it also gives the solution of the one electron Kohn-Sham equation in a basis of Kohn-Sham orbitals, and also the corresponding energies for each of these orbitals. And so the first way that we can sit and take a look at what does the electronic structure look like in the material is to look at a density of states. And so the density of states describes where in energy are the available electronic states that may or may not be populated. And so the spectra on the bottom left shows a red-filled set of energy states, which is the valence band. And then there's an unfilled empty set of states, which is the conduction band within the system. And so having an idea of how the states are relatively separated and sorted can give us an indication of what types of optical energies are going to be needed to promote an excitation and also corresponding emission events. And so that leads us to the next step of we're interested in what the absorption spectra of a system might be. And so the first step in this is calculating the transition dipole moment, which is presented here as Dij. And it's a dependence on the spatial configuration of two specific Kohn-Sham orbitals, the electron density of them. And so here we're interested in one transition between two separate orbitals. And this is also done in an approximation of independent orbitals. So we're not necessarily interested in a superposition of transitions for one excitation energy, but solely looking at these two states. And so this transition dipole moment is then used in calculating the oscillator strength, Fij, which is then used as a weighting factor to provide the absorption for that specific transition. Okay, and so this is the basic ground state non-spin polarized type of electronic structure calculation, but there are also other types of methods for calculating the ground state that can be used, and these are done by installing VASP with different builds to produce them. And so this is just a comment now. This slide, and I forgot to build one for spin polarized. So I'm going to give a general summation of the two methods and then rebuild these two. So the other two methods that we're interested in are spin polarized type calculations. And so when we're interested in electronic configuration that produces triplet and doublet type electronic states, this type of spin polarized calculation can provide us with information on how the two spins may differ in their possible energy states that can be sampled, and also the absorption and emission events that may occur specifically in those two spin states. A third type of calculation, which goes even further than the spin polarized calculation, are non-collinear spin calculations. And so specifically for the cases in which I'm interested in, this is needed because specific materials with heavy elements require the implementation of spin orbit coupling calculations. And so the results of the non-collinear spin calculations are provided again in the basis of Kohn-Sham orbitals, but instead of these orbitals being dependent on only one electron and one spin, they're a two-component type Kohn-Sham wave function dependent on both types of spins, resulting in a superposition of two different orbitals and an energy that is separate than just the two spin components comprising this non-collinear wave function. And so with the solution of these different spin polarized and non-collinear spin wave functions, we can use them in the same type of process I described for finding the absorption of a material. So when we've looked at the ground state electronic structure of a material, when we're interested in different electronic relaxation mechanisms, there needs to be atomic motion. For any type of non-radiative transition that's facilitated by nuclear motion, we need to somehow simulate how these materials are moving at an atomistic level. And so to do this, we run heating and molecular dynamic calculations set for some specific temperature that we desire to know about. And so we're able to take our optimized structure, set our ambient temperature, and allow this set of atoms to be have their velocities rescaled to try to come up and equilibrate with the energy for a given temperature. And so once we're happy with a sustained energy for the specific temperature, we're able to take the velocities of the atoms and use them as the first step for molecular dynamic trajectory. And so we're able to let a molecular dynamic simulation run along a ground state trajectory and record atomic positions at a specific time interval for generally 1 picosecond. And so one of the results in combining the absorption calculations and also our molecular dynamic simulations is that we can look at a molecular dynamic photoluminescence result. And so what I'm showing on the screen are the fluctuations of Kohn-Sham orbital energies, which were the solution to our initial optimization. And so if we would pick the HOMO and the LUMO as our two orbitals in which we're interested of the transition, we can calculate the absorption, the oscillator strength and the absorption value at each instant of time. And then if we look at a total summation or time average along the entirety of the trajectory, what we're able to do is to get some type of emission spectra taking into account the nuclear motion of the system. And so this can solve for issues seen in line widths of calculated spectra that are too thin and account for the inhomogeneous broadening. And so moving forward from that, we haven't even discussed the types of non-radiative relaxation, which I mentioned in one of the very first slides. And so to do that, again, we use the individual wave functions that we calculate along the molecular dynamic trajectory, and we do a comparison between the two, which would result in our non-adiabatic coupling values. And so here you can see in the middle image, there are gray looking walls. And so for each of those gray walls is one instant of time along the molecular dynamic trajectory. And so at each of those time steps, we calculate the total wave function, and we look at how the overlap or how the wave functions compare from one adjacent time step to another. And in between time steps, this produces the non-adiabatic coupling value. And so this is again represented in the right image, where if you would just take one vertical cut as an instant of time and compare it with the adjacent, it provides a coupling. And so once we have this type of non-adiabatic coupling calculated, we need to take that and try to use it towards the end goal of calculating out rates of non-radiative relaxation. And so taking an autocorrelation of this non-adiabatic coupling and then performing a Fourier transform provides us with components that make up the Redfield tensor. And so this Redfield tensor allows us to find the relative transitions for a non-radiative process between individual sets of orbitals that we're interested in. And so this Redfield tensor is also used within or used as a parameter within the equation of motion for the electronic degrees of freedom. And so what we're trying to do is we're trying to take the nuclear motion and see how the motions themselves affect or direct the electronic system themselves, and how the transitions are going to vary depending on what types of motion are available. And so we're able to look at how the electron density matrix is going to change in time in relation to the nuclear motions of the system. And so once we are provided with this type of solution with the Redfield and the Liouville superoperators, we're able to diagonalize it, producing eigenvalues and eigenvectors for the system. and use these in solving for expansion coefficients for some initial excitation or initial condition that we're interested in. And so what we're able to produce from this type of calculation are a couple different things. Primarily, we're interested in the non-radiative relaxation dynamics shown in blue, but we can also take out other types of information about photoluminescence events and look at a time-dependent photoluminescence. And so if we're interested in the non-radiative relaxation rates, so like I said, we can take some type of initial condition for specific electronic relaxation and then allow the dynamics to move the charge in space and time. But what we're really interested in is solving for, is the energies of each charge carriers during the migration. And so by calculating the expectation values of energy, we're able to normalize them and then fit or find a fit for this average expectation value, and then find a rate corresponding to this fit. And so that's given as KE down in the bottom right. And it's also the same for holes, as we don't treat them well, they're not treated with any interaction between them, but they're treated exactly the same. They're through the same formalism. And so once we have an idea of how the charges are moving in time, how this density matrix is evolving, we're able to calculate where in energy they are, and we're able to calculate the transition possibilities during the trajectory. And so here, with a time-integrated photoluminescence, for each instant of time, looking where the electron and hole are, we can calculate the relative energy difference and the oscillator strength for the transition and integrate all emission events along the trajectory. So the last type of methodology that I want to highlight is a multi-exciton generation process. And so this is a process in which I initially mentioned we have one high energy excitation. And so the high energy electron, before decaying through non-radiative or radiative processes, can interact with a secondary charge carrier to produce a second electron. And so this calculation is done done by a collaborator we have and applied to one of our perovskite materials themselves. And so the main things to highlight within this type of calculation are the volume of the simulation cell, looking at transition density, and the Coulomb and momentum space, as well as making sure that it abides by rules of conservation, looking at the resonance condition and density of final states.
John?
Yes.
Sorry to interrupt. Several places in your talk induce a wish to ask you about Fermi's golden rule.
Okay.
Do not answer now to save time, but be ready to address it or to refer to it in several places.
Okay.
How this equation is connected to Fermi's golden rule?
Okay. Okay. And so, in moving from how we're interested in, or how we're going to approach these types of problems and looking at the dynamics within a system, I haven't really mentioned too much anything about the actual confinement effects stemming from spatially restricting how big a material can be. And so when we move from a bulk regime to a quantum confined regime, there are a number of basic principles that can modify the electronic structure of the system. And so this is an incomplete slide. But when we're thinking about what happens to an electronic structure when the system is confined, we end up with larger energy spacings within the material. So this discretization of states prompts the opening of band gaps and increases the energies between adjacent electronic states, which also affect rates of non-radiative relaxation. A second thing is because these materials become so small, they can get to a size where they're smaller than the exciton Bohr radius. And so this is the relative size of an excited electron in hole. And so when a material is bigger than this radius, you can have delocalization or more of a delocalized state for the exciton. But when you start confining it, it can prevent, or it can what's where I'm looking for? It can prompt various interactions that wouldn't normally occur within the material. And so here we're interested in a number of possible effects stemming from spatial confinement within a range of materials. And so one of the things that we can look at are one of the things we can look at is the microstructure of a system. When we keep reducing the size of a nanocrystal, what happens to the specific coordinations of the atoms, and how does that affect observables? For example, how does decreasing size of a nanocrystal modify photoluminescence? And also, how does change in temperature modify the photoluminescence in these small materials? I mentioned energy spacing. How can we utilize opening band gaps and separating states to our benefit? We may be able to take these openings and gaps and functionalize surfaces to add new energy states, which can promote new types of new relaxation pathways within the material. I also mentioned with the energy spacing the energy difference between adjacent states with this type of energy spacing. Processes such as non-radiative relaxation are expected to decrease, and so you're going to have a change in the rates for specific processes just by confining material. And corresponding to that, if you start to slow down one process, are you able to possibly promote a secondary process to be the dominant relaxation pathway? So to look at changing the microstructure, there was a study done by collaborators of ours looking at the change in photoluminescence with temperature and silicon nanocrystals. And so we looked at 3 different diameter silicon nanocrystals shown on the right, ranging anywhere from close to 1 to 2 nanometers. And so in terms of addressing how does the microstructure play into this type of luminescence change, we can highlight the different coordinations of the silicon atoms within the system. And so on the left, you can see there are silicon atoms coordinated to 4 other silica, circled in green. There's silicon coordinated to 2 other silica and 2 hydrogen, circled in blue. And then there's silica coordinated to 3 silica and 1 hydrogen in red. And so the varying levels of coordination for these silicon atoms are going to directly affect the amount, or affect the forces felt during molecular dynamics, and possibly restrict certain motions for the materials. And so one thing that happens and is more pronounced in very small materials is the percentage of silicon atoms that make up the surface. And so the surface atom percentage can be seen going from about 83% for the smallest silicon nanocrystal down to 44% for the largest one. And so during dynamic calculations, we're able to look at both the total movement of the atoms themselves and also the corresponding energies within the electronic structure. So on the left, we have the three models for both a low temperature, 77 Kelvin, and high temperature, 300 Kelvin molecular dynamic trajectory. And so these images are a superposition of all atomic coordinates along the molecular dynamic trajectory. And you can see that for the high temperature, there's a much greater fluctuation away from that geometry equilibrium calculated during optimization. And so corresponding with these types of motions are the fluctuations in energy. And so the low temperature versus high temperature energy fluctuations show that for low temperature, there's not as pronounced amplitude of fluctuation in the energies. And there's also an opening of a subgap in the conduction band up above -3 electron volts. And so the maintenance of, or maintaining this subgap, and also the fact that for high temperature fluctuations, you can see that the band gap closes slightly just because you have energies going up and down, changing where the band edges lie. And so based on this information, we can calculate the molecular dynamic photoluminescence for this three sets of materials at the two different temperatures. And so for the low temperatures shown in the left panel in solid lines, you can see that the intensity is greater than that calculated for the high temperature trajectory, which is the dotted lines. And so how is it that we can possibly look to explain how the microstructure can directly influence the photoluminescence of the material? And so the plot on the top right is a visual representation of looking at the exact values of total change in intensity, the intensity maxes as a function of diameter for the material. And so the blue line plotted there is a relative ratio between intensity maxes for the materials themselves relative to the initial intensity. And then the red is a second fit in trying to account for how does the percentage of surface atoms play into what the projected intensity change might be for a given temperature change. And so you can see that the trends between both of these fits is relatively similar, identifying that indeed there is some type of correlation between how many of the atoms are greatly fluctuating, and its direct effect on the photoluminescence of the material. Okay. And so the second thing that we kind of want to mention, and also alluded to in the Kohn-Sham energy fluctuations, is the fact that band gap energies are going to change as a function of size within the material. And so what I'm showing here are three density of state plots for the silicon systems. So you can see with the populated and unpopulated states that the band gap decreases as the material gets bigger, which is something we would expect. And so the band gap values themselves are listed in the left table, going from 3.6 down to close to 2 electron volts. Now, this isn't the only thing that can affect the band gaps in the materials. We're also interested in how surface functionalization of the material can have this type of electronic structure effect. And so what I'm showing here are band gap values for a range of titanium polyoxotitanate clusters with different surface functionalization. So you can see for the smallest models, down for a cluster made up of 6 titanium, the band gap is up to 3 electron volts, and gets a little bit smaller for clusters that are made up of 14, 17, and 18. And so to go a little bit further into this, I want to highlight two different types of titanium polyoxide titanate clusters. So here we're interested in a TI-6 system and a TI-17. And the reason we've chosen these two systems is because of the electronic structure due to the specific surface functionalization. So for the TI-6 system, it was functionalized with both acetone and propanol. And you can see the density of states for both of these shown in the top right. So acetone in blue and propanol in red. And you can see that for the acetone functionalized system, it actually has population up above the original band gap, which is more or less producing a band gap of 0 with minimal energy difference between the highest occupied and the lowest unoccupied. With the propanol in the system, there's an open band gap, which can be used as a semiconductor for different types of photocatalysis or as some type of electrode. On the bottom is a little bit larger with propanol and methanol functionalizations. And so the density of states on the right, bottom right, shows for propanol, there's an open gap similar to there was for the TI-6. However, now with methanol as the functionalization group, there's an introduced energy state within the band gap that leaves a band gap close to 0.57 electron volts. And so this newly introduced occupied state is going to give us the potential for low energy absorptions, which is ideal for titanium dioxide, as they're primarily have a band gap close to 3.2 electron volts. And it's also going to give us possibility for new relaxation pathways. And so in looking at the Kohn-Sham orbital energy fluctuations and possible charge carrier relaxation, for the left fluctuation image, which is for the TI-6 propanol system, you can see that the structure stays relatively consistent during the dynamic trajectory, whereas the fluctuations for the TI-17 methanol system, you can see there's a very large change to one energy fluctuation. So in looking at the charge carrier dynamics of the system, the bottom 4 left initial conditions correspond to the 4 strongest electronic transitions in the ground state. So there's some type of initial excitation going from, say, 155 to 180, that top left panel, and then the corresponding relaxations for the hole and the electron occur over a time period of about 10 picoseconds. Or sorry, it was about 6.5 picoseconds. And so both the electron and hole are found to relax at a very similar rate, and so the charge carrier separation lifetime is not very large. However, if we move to the TI-17 system, we're looking at excitations that occur or generate a hole in the valence band that now needs to overcome the large subgap due to this newly introduced state. And so the electronic relaxation mechanisms you can see occur on a time scale of anywhere from 200 femtoseconds to about 1 picosecond, whereas for any hole generated inside the valence band that's not the HOMO, it takes a very long time to relax up to the HOMO. So you're looking at hundreds of picoseconds. So this gives a very large charge separation lifetime for the system. And so having this large lifetime can allow other types of photochemical events, some type of redox reaction to happen, potentially on the surface of the material. One of the things that may contribute to this is looking at the partial charge densities of the transitions themselves. And so the HOMO and LUMO for the two systems are shown to go from, on the HOMO are localized somewhere on the ligands, whereas the LUMO is localized somewhere on the titanium core itself. So the majority of these types of transfers are classified as metal to, or from ligand to metal type charge transfers within the system. And so moving now, we want to take a look at a direct comparison of calculations between a bulk and a quantum confined material. And so to do this, we're looking at methyl ammonium lead iodide perovskite materials, which are newcomers to the photovoltaic game and have been extensively studied in the last 8 years with efficiencies going up to 22%. So to look at the bulk material themselves, we're interested in a perfect material, but we're also interested in the electronic changes that may occur with some type of vacancy change. So the simulation models are shown on the left for the vacated model. So the two-dimensional slice shows a missing lead atom, which is removed from the system. And in the three-dimensional image, it would be right in the middle of that simulation cell. And so by removing this type of, by removing the lead atom, it produces a number of interesting electronic environments. The removal of the lead also removes 2 valence electrons, which need to be replaced into the system for the calculation. So we have a perfect system for one. Our second system is just has the lead removed and no charge correction. The third system has 1 electron added back in, and then the other system has both valence electrons added back into the calculation. And so we're interested in how this changing electronic environment will affect the electronic processes in the material. So the top right set of panels shows the density of states for the closed shell electronic structures. So these are the perfect system, the lead vacancy system with no charge correction, and then the lead vacancy with 2 additional electrons placed into a singlet configuration. And so you can see in comparing the pure and the lead vacancy, you can see the introduction of a new state in the band gap. And so this new state can lower the absorption onset, and also cause relaxation pathways to be lengthened, as there's going to be a subgap going from the conduction band to this LUMO state. And then in the singlet configuration, you can see that the band edges at the valence band push back up, which is in agreement with the charge density being localized on the lead and iodine at the band edges within the material. Now, this is done in a 3x3x3 supercell, which results in a direct band gap away from the gamma point of the system. And so to correct for this type of, to show that yes?
May I interrupt you? So for curiosity, when you have bulk perovskite, the lead ions contribute orbitals to the bottom of the conduction band. And you can mention them, like 5s.
Okay. Yeah, I'll put
something like this. And here's the question. If you remove 1 lead ion, you also remove this 5s orbitals from the bottom of the conduction band. Why? You observe formation of the trap state in the middle of the gap. What is the hypothetical mechanism of the trap state formation? Do not answer now, it may take longer.
Okay.
Okay.
So you want to, all right, so you're asking about with removal of the lead, removal of specific orbitals, and why it creates inside the band gap, correct?
Yes.
Okay. I'm going to think about that. I'll try to answer it by the end of the presentation. Okay. One other thing to note here on this slide before I move on. So when we're looking at this vacancy system, even with the inclusion of all K points, we still find that the vacancy persists within this band gap, which is something that the reviewers were wanting us to share. So because we were looking at how the electronic structure varies by K point, we did some band structure calculations for the system. So here, again, I show band structures for the closed system with the lead vacancy, and then the charge-corrected singlet electronic structure. So a couple things to note. So we have a flattening of the bands as we take away this lead atom and the corresponding electrons, and we get an even flatter structure once we introduce these two charges back in. But the other thing to note is that we have this persistent vacancy state that doesn't change much as we change between different K points. So regardless of where we're taking or calculating these energies, we're always going to find this type of structure. And so I think I'm going to remove this other picture here and just have it as extra information. And so because we were looking solely at the gamma point, and we knew that the band gap energy didn't match up with that of experiment, the absorption energies shown on the top also show absorption onset at a much higher energy than we would expect. They correspond with the calculations, but not with experiment. So again, to introduce the concept that multiple K points are necessary for the correct electronic spectra, the bottom four right panels show K point corrections for the vacancy and the charge corrected state. And so here, the top two have the total absorption spectra, which have their onsets 800 to 900, which is ideally with what we would want to see, with the bottom two panels showing the individual contributions to absorption by each single K point calculated for the system. Also noted is the fact that we hadn't used spin orbit coupling corrections, which is necessary in these types of materials. And so, and to try and appease some of the reviewers, we worked in calculating the absorption spectra with spin orbit coupling. And so for the systems, you can see that the spectra themselves don't change much in shape. The majority of the change occurs only in energy shifts. And so when looking at other types of calculations done for the spin orbit coupling, we know that different bands at the bottom of the conduction band are going to split, reducing the energy of one instead of having a degeneracy. And so this is one of the things that is a primary contributor to this shift in energy. So when looking at the open shell electronic configurations, we're able to look at the alpha and beta spin projections separately and independently of one another. So the absorption is shown with a total spectrum in black and alpha and beta as red and blue dashed lines. And the red and blue also correspond to the density of states shown for the structures below. So with the spin up and spin down, you can see that there's a non-symmetric component to the shape, whereas the beta components are showing an empty unoccupied orbital within the system. And so this unoccupied orbital will produce dynamics similar to that of just the vacancy closed closed shell system, as they both have an unoccupied state within the band gap. Now, with the addition of multiple K-point calculations, the major difference occurs in the shape of the bottom of the conduction band. And so there are extra states that are added in at the bottom of the conduction band that may lead to different rates calculated out. So during dynamics of the systems, we're able to look at how these energies fluctuate as we have in the past. And so for the systems studied, there wasn't large fluctuations in energy amplitude for the majority of the systems. However, for the lead vacancy system itself, there was a drastic change of having the LUMO orbital very, very close to the top of the valence band, and also have a very large fluctuation in energy. And so this is something that we looked at, and we contributed to the formation of an I2 molecule at the vacancy site within the system. And so looking at the dynamics of the material for all different sets of systems, the open shell are the top four. The bottom three are for the closed system. And so if we start with the closed system, you can see for the pure material, the holes are relaxing somewhere close to a picosecond or less, whereas the electrons are just slightly longer than that, which experimentally are expected to be anywhere from 500 to 800 femtoseconds, so it's on the right time scale. But once we introduce this lead vacancy, you can see that there's a much longer lived electron lifetime, promoting this charge carrier separation lifetime. But then when we move back to adding the additional electrons to correct for the charge, the lifetimes are relatively similar, but just shifted to be a little bit longer. For the open system, there is some correlation or mirroring of what happens in the closed system. For the lead, with one additional electron in the spin up, it's similar to that of the pure, with electron hole relaxing on similar time scales. But as soon as you look to the beta state, which had the extra unoccupied state, you have a very long lifetime for the electron, as it has to move down to the conduction band and then jump the subgap to this LUMO. And then conversely, for the triplet state emissions, there can be variations in subgap for the electrons and holes, but still, for the alpha component of the triplet state, there's two additional electrons just inside the top of the conduction band. So any type of relaxation of hole is going to have a very large subgap, which is seen in blue. Whereas for the beta component, the timescales for the electron and hole are going to have a very long hole time scale, or sorry, electron time scale relative to the hole, just because of the unoccupied state very, very close to the top of the valence band. And so from these non-radiative calculations, we can also look at the time integrated emission spectra that are produced. And so we have major peaks shown for band gap energies, which is something we would expect, as there's no recombination calculated. Once the charges hit the band edges, they stay there until the calculation is done. But one of the interesting things for the triplet states is that you can still get some strong emission across the large subgap in the system, even though the electrons can still the HOMOs still populate up into the conduction band slightly. And so the same thing can be said for the beta component of the triplet states, where you have a small emission peak that's still very large. So it's skipping that extra state contributed to the top of the valence band. For the closed systems, again, you see large peaks at the subgap energies that are shown, and also for the band gap. And then for the singlet state, where there's no additional electronic states added in, there's just a large single peak at the HOMO-LUMO gap. And so here, don't read the tables. You can just listen to my voice. So the main, I'm going to take most of these out and just provide a few numbers. The main goal from what this table is, this table provides that the non-radiative lifetimes for electrons and holes are generally on the order of 1 to 5 picoseconds for electrons and less than a picosecond for holes, until you get to systems with newly introduced states. Then you have lifetimes that are extremely long, somewhere close to 80 picoseconds, 80 to 100 picoseconds. And so these varying timescales are going to be used to compare with a quantum confined piece of the material in a little bit. One of the other things I want to note, though, was in looking at these different spin components, we can estimate, not predict, but just have some rough estimation as to what a quantum yield for that material might be. And so with the materials that have more or less no additional state within the middle of the band gap, you can see for the spin alpha, you can see for the triplets, or the singlet, and then for the beta triplet state, you can see that there's very large quantum yields. So without having some sort of trap state in the middle, you get some relative scales of non-radiative and radiative emission. So to do the correct comparison, we also studied a spatially confined piece of the material. And what we did was we took just 3 unit cells and built this almost nanoplatelet type piece of the material. So as it spins, you'll see it's kind of almost like a 3-dimensional triangle type piece. And so looking at the ground state structure of the material, we can see that the band gap's at 2.1, which for spatially confined materials, we expect that there's no dispersion, and we're looking solely at the gamma point. And so the fact that this band gap is greater than the experiment is expected compared to the bulk material, which was just shifted away from the gamma point. And so another thing that we wanted to take a look at was during optimization of the material, if we start from this cubic structure, the cubic structure is known to be the high temperature geometry. And so during optimization, we're going to see some type of restructuring to a different geometric phase. And so the ground state distributions for the 3 different phases are shown, and then also an overlay of the calculation for along the molecular dynamic trajectory to determine if the structural shape was maintained, which it was. And so in looking at, or in considering multiple different relaxation mechanisms, we've already been looking at non-radiative relaxation and radiative relaxation. And so when we're interested in these types of relaxation rates, we're looking also at non-radiative recombination. So we're interested in the specific transition from HOMO to LUMO compared to other types of fast rates. And so this rate of radiative combination is seen to be on the order of 100 picoseconds, shown highlighted in yellow, the transition from LUMO to HOMO. But then we're also interested in the non-radiative relaxation rates, which, as we would expect the spacing to increase in the quantum dot, we would expect the non-radiative rates to slow down, giving them longer lifetimes relative to the bulk material. And so when we look at the time scales for low and high temperature, you can see that for holes and electrons, instead of looking at, around 1 picosecond, now instead we're looking at things that are anywhere from 1 to 10 picoseconds, or 5 to 10, or even higher than that. And so there should be a slide about the MEG results in there. So in looking at the timescales for these different types of relaxation processes within the quantum dot, the calculated rates for the multiplex time generation were somewhere on the scale of 10 femtoseconds, whereas radiative or luminescence were on the scale of both 10 picoseconds and 100 picoseconds respectively. But then looking at the non-radiative relaxation and the non-radiative recombination, they're on the scale of about 5 picoseconds, which was longer than what was calculated for the bulk material. But then the non-radiative is on the order of 3 nanoseconds, which is we would expect this process to be the slowest. So with the slowing of this type of non-radiative process, we can give more time for the multiplex time generation, which is a more efficient process, time to occur. And so in looking at all these systems, we're able to find that by confining different types of semiconductor materials, we can highlight that changes in size can influence the coordination and microstructure of a system, which can then influence the dynamics and the availability for radiative and non-radiative events. We're also interested in looking at how, due to the spatial confinement, we can find the opening of band gaps. We can find that the energy discretization directly affects non-radiative relaxations, and also allows for spacing to insert energy states due to surface functionalization. And so these types of functionalizations can also allow for new pathways and events to occur, which can be beneficial for photocatalytic or photochemical processes. And we also looked at in the bulk perovskite materials, the effect of different vacancies and the effects on the rates, and also in relation to confining the material and having a slowing of specific mechanisms allow more efficient types of mechanisms to promote and be dominant, increasing the possible application of the material. And so these are people I'm very thankful for. And I will just end it there. So.
You would have some questions?
Mm-hmm.
So what would be the effect if you were able to include excitonic effects on your spectra on like slide 8, I think?
Okay. So including exciton effects within a material, so you're gonna end up with changes in relaxation rates. You're gonna have changes in band structure shape and energies between them.
What do you mean band structure shape?
Well, so if you have some sort of, so you have a creation of an exciton, right? And so as somewhere they may well, maybe that's not the right way to put it. So depending on the spatial confinement, right, if you get them somewhere reasonably close, you can have a larger overlap of the two exciton particles. And so you would have some type of faster radiative transition, right? Because if you have a larger wave function overlap, you're going to have a larger oscillator strength.
Oh, okay, but what did you mean by band? Because
Well, when I was
people call in vast band as molecular orbital.
Right. I guess when I was thinking about it, so if you're looking at band edges, like the valence band and conduction band, some type of added Coulombic attraction can sometimes bend the valence and conduction band slightly.
So you're talking
energy.
like a PN junction.
Sure.
Well, I do not see connection to PN junction.
If you take PN junction,
You
the
just mean
bands will
Yeah.
Band bending.
Yes.
Yeah.
So will you have the same energy range for your absorption, or will it redshift or blue shift?
I would expect it for absorption. I would expect it to maybe redshift a little bit.
And then do you think every transition would redshift systematically, or would it also depend on the nature of that state?
I would say it probably depends on the nature of that state.
So in your perovskite material, has anyone shown that excitonic effects only shift it systematically, or has no one looked at like T to the FT to look at the excitation?
Off the top of my head, I don't remember, but I know like Amanda has done exciton calculations in perovskite materials, so I can definitely look at that
Okay.
readily. But
We all need to ask John and for his interest, but I'm impatient to answer to Levi. If you noticed absorption spectra that John computed with and without spin orbit coupling, they do have an offset of about 1 eV. So influence of spin orbit coupling is much stronger in this material than formation of bound exciton. And do you have spin orbit coupling included in Gaussian where you do TDFT? So you see, it is possible, but not easy. Please keep asking, John.
I have a question as far as application goes. So, what part of a solar cell that we currently use would this replace? Would it replace a part of a current solar cell, or would it redefine solar cells altogether?
so are you referring to the perovskite materials?
Yes.
Okay. So the perovskite materials themselves would be the photoactive material within the cell. So the material that's absorbing the light and then separating the charges. I mean, the materials themselves are known to be able to separate the charges and migrate them separately without any type of transport layer. So it's just having a material that has a band gap that's 1.6 to 1.7, and then you can stack hole and electron transport layers on top of it relative to. So silicon is what, 1.1, I think, for a band gap energy. And if you look at like Shockley-Queisar efficiency values, I think the highest efficiency possible for a material has a band gap of, I want to say maybe like in the range 1.2 to 1.4 maybe. I would have to go back and look at that plot again. But no, so it's a material used as a photoactive material that's easy to make relatively easy and cheap to make. And Aaron knows a little bit about this now that he's trying to build these types of cells. So.
Okay, so you wouldn't have to redefine solar cells from the ground up. You'd be able to replace.
No. It's just you could use silicon as a photoactive material, which is primarily what most of the industrial panels are made out of. You could take that out and put perovskite in, and then you'd have to change a little bit of the materials for collecting and separating the charges, but it's pretty much a substitution.
Okay, cool. Would you have to change the work function of the contacts?
I would have to look at the exact device design. I would assume so, because you want some type of bias driving the charges to the right electrodes for them to be collected.
That's okay. We're kind of not engineers, right?
Yeah.
Gold is the best. Gold contacts give the highest efficiency.
Cheap.
More questions or objections or comments?
Yeah, probably his talk was more than 1 hour, right? Have you looked at it? John,
Yeah.
maybe you have to cut some part of it because it's kind of too long.
Yeah, that's it's shorter than it was last time, but it's.
So last time it was 2 hours, or
We ran out of time.
John went only over half of the talk, and we spent 2 hours.
Yeah. Granted, we did have questions during, but no, there's a few things I'm going to take out and I'm going to redo just to highlight some of the more important things and maybe not worry about the details.
One place that you could probably cut a lot of time is the slide before all the tables, because I think you spent like at least 5 minutes going over every figure. And I'm not sure if that is that important because you have so much information on that slide.
Yeah. Okay, so that was slide 34.
35, I think.
yeah, you probably don't have to go into the details and several slides. Just
Okay. So if I would give a general description that there are classes of transitions that have an extra state and there are transitions that don't, that would be sufficient.
Yeah, if there was one out of here that does, you could say, if we look at these specific type, boil it down and say these have 2 transitions, these have whatever, like intermediate. It's hard to see. It's kind of small on the paper.
Yep.
Also, maybe slide 10 when you talk about heating and molecular dynamics. You went really in depth on that as well. Maybe you could cut that down, the explanation of it, cut that down maybe.
Okay.
Just because there's so much literature on it that I think that it would be okay to do that.
Not everyone's an expert like you, Dave.
Well, I'm not, but could always look it up, Google it. Oh, and on slide 15, if I can make one suggestion, you have a blue box with black writing. If those colors don't mean anything to you, I'd recommend maybe changing the blue to green or the black writing to white writing.
Okay. Well, I might just take those out.
Okay.
Because they're not really necessary. They're just there.
So I have a conceptual question on 14.
Okay.
What type of basis are you in? Are you in diabatic or adiabatic?
For 14. So, so these calculated along an adiabatic molecular dynamic trajectory.
So does the monitoring the band itself influence your electronic dynamics, or is it totally it does not matter about the band, even though you may have band indices switch
Right,
because
right.
of the
So
fluctuation.
there's definitely going to be some indice switching happening, but the way, well, so it's an average over the trajectory, and but to answer your short question, no, or short answer is no. That's not taken into account that there could be indice switching. It's just kept as state 1 to state 2.
And then what causes the bands to fluctuate at different rates? Because if everything fluctuated at 1, you would have a single
Right.
function. But here, yeah.
Okay. So, right. So so the solutions that result in the cone-shum orbitals and their corresponding energies, right? So you can image the cone-shum orbital through some type of partial charge density, and so looking at the localization and which atoms and orbitals are contributing to, say, that molecular orbital hybridization. So if you have, one hydrogen stretching rapidly on one side of the system and another one stretching at a slower rate, if that cone-shum orbital is localized on the fast stretching, you're going to have a large energy fluctuation, whereas if you have something localized on a slower stretching, the energy probably won't fluctuate as much.
So in other words, it's electron-phonon coupling.
It's, the nuclear effect on the energies.
So on slide 32 for your absorption spectra, comparing spin orbit coupling and spin polarized.
Okay.
So for the first, the one where you charge it with 1 electron and 2, it looks like both of them have the same absorption between spin orbit and spin polarization. So is there a reason why behind that?
Oh, so you're comparing images from slide 31 and slide 32?
No, just 32.
32?
So, okay.
John, slide
Yes.
32, lowest row, image number 3, which is labeled with letter C.
Yeah.
Okay. Oh, sorry. My slide numbers are different in this version. Okay. Okay. So we're looking here. Can you see my screen again? This is what we're looking at.
Yeah.
Okay. So you're asking why those two absorption spectras look the same?
Yes.
Which ones are we looking at? A, B, C, D.
C.
So we're looking at
B.
C.
Or just C.
so B is it's not a spin polarized. It's just a spin restricted. There's no additional electrons here, so it's a singlet. C is a 1 electron spin polarized system. It's a doublet, and so
I want the intensity of the beam.
yeah. So I guess what is exactly your question now?
So like if you look at around like 1 eV,
Yep.
it kind of looks like that both spin orbit coupling and spin polarized transitions occur there.
Right. So within this one additional electron state, if we look at the density of states for the spin polarized, right, we see that the alpha component looks pretty normal, but the beta component has an unoccupied state, like here. So you can see that there's an unoccupied state here at about 1.5 eV. So that low energy band, absorption band for the beta is occurring from somewhere in the valence band to here. But also because the spin orbit coupling takes into account, the alpha and beta spin mixing into its orbitals, it's going to have some component of beta taken into account, meaning that if we would look at the density of states for the spin orbit coupling, I would also expect to see some type of unoccupied band just above the valence band, somewhere that would correspond to about the same type of absorption energy. Right, because here, right, yeah. So when we have this wave function for this the spin orbit coupling, it's comprised of the two components for up and down. Does that make sense? Or
Yeah,
maybe
somewhat. I guess my initial thought was just, since it's a vacancy, it's just a dangling iodide bond. So like spin orbit coupling wouldn't contribute to that. Well, it would be negligible compared to if it was a lead orbital.
Okay. Well, and so that could also be to the point where there was a question about where. So if you remove that lead atom, you're also removing the orbitals for possible electronic population. So it could be that if it's the case where because we remove this lead electron, the vacancy is then pushed to somewhere off of lead that's it's still in the system somewhere, that even with the spin orbit coupling, it could still manifest itself. But maybe someone else has a better idea too.
Yeah, I don't know. I'm not satisfied, but I'm not sure where the disagreement lies. So
Yeah.
I'm not really sure what to say.
Will it be possible to generalize and tell that there is a class of states or class of excitations when spin polarized and spin orbit qualitatively coincide, and then we can reduce computational cost and do everything with spin polarized? It will be very pleasant, very helpful, but hard to believe. At least in this specific case, they coincide, and if you would have more states, we can prove a theorem like forget spin orbit, do old good spin polarized. Do you have something to ask, John?
I guess maybe not right now. I will write him an email because I have lots of questions.
Okay, so if you that's right. So please consider to scan and send your questions to John. If you do not feel enough steam to scan, you can give it, let's say, to me, and I will scan. But then he will answer thank you only to me. If you send it personally, you get a personal thank you. And also
that's not true.
There is a question to John. We started to discuss it, but it was not yet shaped out. How to help audience to navigate? What connects different parts? Most of us were witnessing the defense by Brendan Gifford, and at later stages of later drafts of his thesis, he made a map that helps audience to navigate. So can you just consider the flow chart that will make like lines connecting and explaining what the parts are? While listening to I did try to do something, but I can be very wrong. So you are the author, I can just suggest. So one flow chart is for methods. So you have three big blocks. You throw in atomistic model, then another big block is ab initio calculations of different DFT, molecular dynamics, and Redfield. And then it gives three types of observables. So this way you mimic the experimental instrument and replace a whole big lab with just a set of with a cluster with the right software. And another thing, you may connect which models you touched. And again, I can be wrong, but you have most of them are quantum dots, confined perovskite, silicon, and titanium dioxide. And also for perovskite you have bulk, and for titanium dioxide you did some nanowires and bulk or surfaces before, but you don't cover them in thesis, but maybe, well, try to think to help audience to follow simple map, simple route through this long thesis or long presentation. Are there more questions? John, please.
Do we have other stuff after this, or
No.
okay? So on where you have the broccoli plots, why does the smaller systems vary a whole bunch more, even though on your methodology slide you use stat thermo to say that the sum of the kinetic energy is equal to 3/2 n Boltzmann factor times temperature? Wouldn't that mean that everything is scaled similarly? Therefore, you should not get more displacement in the small systems compared to the large systems?
Okay. So one answer to that question is directly relating to our interest in the microstructure and how the percentage of surface atoms change as you keep shrinking the silicon nanocrystal. So for the smallest crystal, you have the highest percentage of silicon atoms somewhere on the surface. And so these are the silicon atoms that have an under coordination. So they're either coordinated to 2 or 3 silicon atoms instead of 4. And so you have a larger, you have a less rigid silicon atom at lower coordination numbers, allowing for larger fluctuations in atomic position. Does that make sense? Like if you have a really big piece of material and you hit it, the atoms in the center aren't going to move at all. But if you hit whatever you hit on the surface is going to have the greatest movement. So
what you're saying is the surface potential is lower than the core potential.
What do you define as potential?
So if you move the atom, it's easier to move the outside than the core. Because then that would go directly into the derivative of R.
That's right.
Right, the velocity.
Surface atoms,
velocity
they have
of it.
less bonds. They
Okay.
easily
More degrees of freedom. They can move sterically in all dimensions.
That's right.
And the bulk atoms are confined, and they can do only small oscillations.
That's right. That's what's
Physically, it makes
Great,
sense.
great answer, John. I didn't think about that.
Okay.
I was wondering the slide 24 or 25, I don't remember. This functionalization, the surface functionalization, why the propanol has the smallest band gap, I mean, in case of the propanol. The titanium 17. There is a table.
Right. So, okay. So because the that could be because I mislabeled it. I bet that is exactly what it is. That should be methanol. I have the propanol and methanol numbers mixed up because the density of the methanol, if you look at the density of states, it shows that occupied state close to the conduction band, whereas the propanol is open. That's. Thank you for pointing that out. That was my mistake.
That's methanol.
Defense is canceled.
As you say, we've got about 1 minute, if my memory serves correct.
Good talk.
Thank you for elaborating.
Yeah. But
So
I can always.
we are going to get cut. I don't remember either in 1 minute or in 11 minutes, but the connection will will be disconnected by how the stopwatch is set up by
Your call will
university.
be disconnected.
Okay, 1 minute.
Okay, let's thank John once again.
Thanks, guys.
Success.
It almost sounds like you're not going to it, Dimitri.
I have